Okay, I will continue with the Perron-Frobenius theorem, which I was halfway improving yesterday. So I will start with that part for today. So the Perron-Frobenius theorem, if you recall, is where we have a non-negative matrix that is irreducible. Then the main point is that the last eigenvalue of this matrix is also an absolute value, the last eigenvalue, and it has multiplicity 1. That are the number 1 and number 2. So then we have seen, we are going to show now from now on that the theta, the smallest eigenvalue, is bigger or equal to minus the largest eigenvalue. And we also will show that equality if and only if it is bipartite. Then we show something and some technical thing that we need sometime later. That's number 5. And for 6, we can see, for 6 it's important because if you have an induced subgraph of a graph, then the spectral radius is really smaller than the of that induced graph is really small than the original graph. That is the main point of 6. So we already have done 1 and 2, so I will not repeat them. So we have done yet yesterday. So we start with 3. So we want to show that the theta min is at least minus the theta, the last eigenvalue, at least. And for that, we need to consider 2 cases. Either c squared is irreducible or reducible. We don't know on this moment whether it's reducible or not. Yes? So if it's irreducible, then we see that theta 0 squared and so on, and theta minus squared are all eigenvalues of theta squared. They can be equal to each other, I don't know, yes, but we don't know. We also know that for the phi that we have for theta 0, we see that it has only positive entries. And then by 1 and 2, we see that theta min squared must be smaller than theta 0 squared, because theta 0 squared has multiplicity 1 by part 1 and by part 2. So therefore, we get that the theta min is really greater than minus theta 0. Yes. So that is the case when c squared is reducible. And now if c squared is reducible, we want to show that the graph is bipartite. So we want to show that if c squared is reducible, then the graph C is bipartite and loopless. That is an equivalent statement. So we assume now first that C is bipartite and loopless, and we have then C this form for some m, and then it's easy to see that C is reducible. Yes, C squared is reducible because you get 2 blocks. Yes, you get the block m times mt and mt times m. Yes, and you 2 blocks. Now we want to show if it is reducible that the graph C is bipartite. So we let I and j be adjacent vertices in the graph we had constructed from C. Then we look at I ought to be the vertices that have odd distance or even distance to I. Yes. You say, yeah, but you have to be careful that means really the shortest walk between the two. Yes, the length of the shortest path between two. So a vertex has still distance 0 with itself. Yes. So then it's easy. Then you can so you can remove the loops if necessary. Yes. So in this graph C squared, the graph you construct from C squared, the induced graph on the odd vertices and even vertices are connected. Why is that? Because the graph is connected. And so, and you can only go with steps of 2, yes? So an odd vertex is always 2 odd vertices. If they have distance 2, you can only go by distance 2 from one to the other one, yes? And then you see that it must cover all the vertices, yes? Because you can go by induction, yes? And then you see also by even. So that means that C squared has at most 2 components. And if it has 2 components, then any distance between any 2 vertices in I odd and I even must have even distance, because if it's odd, then you can go, then they must be all connected. So then it must be irreducible, but we cannot have irreducible. So we assumed it's reducible. So we must have 2 components. So this shows that the EC is bipartite without loops, and this shows the claim. So this shows that maybe I should have said the graph T. I missed. That is the graph. The T means the graph constructed from C. Okay. So now we will show that if C squared is reducible, that theta mean is minus theta 0. This is what we did before. We know that the graph is bipartite. The graph T is bipartite, so we have the red and the blue vertices. And then we can see that we did this trick already before, and now it still works. And this shows that we have 3 and 4. Yes, that the graph T is bipartite, and therefore, if it is reducible, then the TC is bipartite, and then you must have that theta min is minus theta 0. And this shows 3 and 4. So now we do the technical 2 things. So we assume x, a vector x that has only non-negative entries. It is not all 0 vector, and that Cx is at most theta x for some theta. So now we assume there exists a coordinate where xk is 0. So then, because C is irreducible, we may assume without loss of identity that there exists an I such that Cij is greater than 0 and xi is greater than 0. Yeah, the main point is, yeah. So, but then we get that this is 0. Yes, we get 0, but that is greater equal to, by the assumption, Cxj. And that is by definition just the That's the sum of these neighbors. Yes. Of yeah. So yes. And that is greater or equal to this entry because all the entries in X and in C are non-negative. So that's always, if it's already one entry is already greater than 0, then the rest is greater or equal to this. So this means that 0 must be greater or equal to 0. And this is contradiction, yes. That's it. And this shows the A part of that part 5. Now we want to show the B part. Maybe I should go back for now to the Perron-Frobenius theorem. I know that this is bad behavior, but okay. So we had to show that the theta is at least theta 0 and theta 0. Theta is theta 0 if and only Cx is theta x. That is what we have shown. So that is where we are now. So this, we have done this now. Now we are there. We have to show that theta is greater or equal to theta 0. So we have the vector phi, and that is non-negative. And we know that there exists a beta such that xi minus beta, and we take beta as big as possible. And we may, this means, so we know that every entry of x is positive. So beta is bigger than 0, but we take beta as big as possible, such that it is greater to 0. Then we must have a k where this in this coordinate is 0. So when we look at x minus theta 0 beta, that is greater or equal to cx minus beta phi. Yes, by definition, because we already have, because for CV is exactly theta 0 times phi. So this is therefore works. So now we use that theta xij minus theta 0 b vj is greater than 0, and that xij minus beta vj is 0. If we use that, then we see that theta. So we replace beta v by xj, beta vj by xj. So then we get the following equation, yes. So that means that theta minus theta 0 times xj is greater or equal to 0, yes? And that means because xj is positive, that theta is greater or equal to theta 0. And as the multiplicity of theta 0 is 1, we see that cx is theta x if theta is theta 0, and this shows the b part. So now we're going to show this part 6. And now we want to assume, now we want to show that we have this situation and beta is symmetric and b is symmetric, I'm sorry. So we want to show if b is not equal to c, then the spectral radius of b is smaller than the spectral radius, strictly smaller than the spectral radius of c. Let sigma 0 be the last eigenvalue of b. We may assume there exists an x greater or equal to 0 such that bx is sigma x to 0 x sigma x sigma 0 times x. And we have this because we don't know b is irreducible or not. But then we look at all the irreducible parts, and one of them has largest eigenvalue of one of the irreducible parts, and then we take that irreducible part, and then it has an eigenvector, and the rest we take 0. Yes. So then we use this Rayleigh inequalities. So we know that theta 0 must be greater or equal to x transpose c x, x transpose x. And that is clearly greater or equal to x transpose x. And that is sigma. So we get that theta 0 is greater or equal to sigma 0. That is easy. But now we want to show if sigma theta 0 is equal to sigma 0, then B has to be equal to C. Now we assume theta 0 is sigma 0. Then without loss of generality, we assume that x is 3. Why? Why may we assume that x is 3? Because theta 0 is x transpose cx, x transpose x. And there's that eigenspace for theta 0 has dimension 1, so it is spanned by phi. So we may assume that we can take x is equal to phi. Yes. So we get this equality, yes. And this, why do we get this? Because phi has only positive elements. Yes. So if phi of p is really less than c, then we get here strictly inequality for this inequality. Yes, so that is the main point, that because otherwise you cannot get equality. Only the way you can get equality in this inequality is taking b equal to c. So that shows that if b is not equal to c, sigma 0 is strictly less than theta 0. And this finishes the proof of the theorem. That was a long proof, I'm sorry. So the Perron-Frobenius theorem shows that the last eigenvalue of a graph is also the last in absolute value. And this is the reason why spectral radius is called spectral radius. And the sixth item of the Perron-Frobenius theorem shows that if you have a proper induced subgraph of h of t, that has always strictly smaller spectral radius than spectral radius of t. So it is more, we will show later interlacing, but this shows that here's always that you get here not only in inequality, but you get really strictly inequality for the last item. And the third and the fourth items show that if a connecting graph is bipartite, even only its small eigenvalue in absolute value is equal to its spectral radius. Okay, that was the Perron-Frobenius part. Now I will start with equitable partitions. This will be not so difficult, the equitable partitions. So I will start with this. So I will see how far I come today, and then we see how far we come. Yes, we are looking at partition of a graph, of the vertex set of a graph. And we want all the paths not equal to empty. We don't like that. For me, a partition is where all the paths have non-empty, are non-empty. and are disjoint and cover everything. That is what a partition is, yes? So now if we want to use the term equitable, if you take two vertices, or you take a vertex X, and you take a part Tj, in J, a part of it, then the number of neighbors of X in Tj is only depends on which part X lies in. And that is what it is. So if X in Ci, you take any X in Ci that always have exactly beta ij neighbors in Tj. So I'm sorry. So that means that Ci is a regular graph with valency beta ii. And if I look at the graph between the Ci and the Ck, that is a bipartite semi-regular graph. There are maybe two different valencies, maybe one valency, but we have one phase from one side and one phase from the other side. Yes. And with V, we will denote the quotient matrix. That is called the quotient matrix of pi. We will define a quotient matrix for a general partition later, but now I only do it for an equitable partition. And how can you get equitable partitions? You can look at orbits of a group of automorphisms. Yes. So you look at the permutation on the vertices that leaves the asset in, leaves its asset. Yes, that is all what I'm saying here. Yes. And now I take a subgroup of that automorphism group, and I look at the partition consisting of the orbits of the action of gamma on G. And say that has orbits O1 up to OT, and now I look at the partition. That partition is equitable. That is because the group is a group of automorphisms. So I will give some examples. I will look at the Petersen graph. I think everybody of you know the Petersen graph. If you did not see the Petersen graph before, here's the Petersen graph. Now we look at the group generated by the permutation 1, 2, 3, 4, 5, 2, and 6, 7, 8, 9, 10. I hope that you understand this notation, what I mean by. So that means that 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, and 5 goes to 1. And 6 goes to 7, and 7 goes to 8, and 8 goes to 9, and 9 goes to 10, and 10 goes to 1. Or 6, I'm sorry. Then this has two orbits, namely O1 is 1 to 5, and O2 is 6 to 10. And you see that there are 2 5 cycles, yes. So you see that on the diagonal of the quotient matrix, you get 2, 2. And between you have 5 edges, so you see that it is 1, 1, 1. Yeah, the off diagonal entries are 1, 1. Yes, so you get this quotient matrix. So now, so we can also look at the distance partition of a set from a set C of a subset of the vertex set. That means you take C as C0, then you take the vertices that have a vertex, the vertex outside C that have a vertex neighbor in C, that is C1, and so on. You can define C2 at distance 2, C3 at distance 3, and so on. So now we look at the vertex 1 and we do the same thing. Then key, if you do this distance partition, then the neighbors are 5, 6, and 2. And the non-neighbors are the rest, 3, 4, 7, 8, 9, 10. Yes? If you did not see it, check yourself. I already sent the slides to the organizer, so maybe he already distributed to you. So we consider the partition, yes? So the first vertex 1 has 3 neighbors, namely 2, 5, and 6. They are non-neighbors with each other, so they have 0 neighbors in themselves. There's no triangle in the picture graph. So the other 2 neighbors must go to distance 2. If I now take a vertex at distance 2, that's 0 vertices, and the neighbor is not a neighbor of x, so that is 0. Now, but you can see that the induced subgraph on the 6 is an hexagon. So that's a 2 regular graph, and the basic graph is 3 regular. Yeah, in principle, you already have seen that now we have already shown somehow that the basic graph is vertex transitive. Yes, so it is 3 regular graph here, so that's not so difficult to see. Yes, I already have seen that. Yes, you can check the picture one more time yourself. So this is with respect to C, yes. So up to now we have seen of equator partition where the paths are orbits of an outmorphism group of graph. But it's not too difficult to find a graph, even connect graph with an equator partition whose paths are not the orbits of a subgroup of outmorphism group or C. For example, if you have a strongly so if you don't have a vertex transitive graph, many graphs are not vertex transitive but still regular. Yes. If you take a regular but not vertex transitive graph, then if you take the vertex set as your only part in your partition, that is still an equitable partition, yes? With only one part is very trivial, but still equitable. But that is then not an orbit of the graph, yes? So it is also difficult to see this. So we now define the characteristic matrix of a partition. And so that is a V times T matrix, where V is the number of vertices and T is the number of parts, and Pxi if x lies in Ci and otherwise is 0. It's not a difficult kind of matrix. And the book TR is a book Algebraic Graph by Christos and Gordon Roll. It is in the CGM series, but I don't know exactly what is the number, but it is by Springer. Because I'm not in my office, we are locked down in this city, so that's life. So let's see. This is lemma 9.3.1 in the book TR. So an equator partition with quotient matrix B. Then we have AP is equal to PB, and we can write B in a very difficult form, P transpose P, and then the inverse of that matrix times P transpose AP. So we will show this now. So we want to show that AP is the PB. So let U be in Ci and J in a number in 1 to t. Then we calculate APUJ. That is the number of neighbors of y of u, such that they are in, that is number of neighbors of u that lie in Cj, yes? And that is beta ij. On the other hand, if I calculate PB uj, then I see that this is L from 1 to T, PUL, PLI. Yeah. And that is because U lies in CI, so that is BIJ only, and that is the same thing as beta IJ, as PUL is 1 if and only L is I, and otherwise it's 0. So this shows that PB is AP, and hence we can add a P transpose in front of both, yes? Then that is what we get there. Now we need to show that P transpose P is invertible. And that is just on the diagonal, there's a diagonal matrix where the diagonal matrix elements are the number of elements in CI. Now this is the reason why we don't want empty parts. Yes? And otherwise it's 0, it's just a diagonal matrix. You can read the equation, yeah, but that is not so difficult. Yes. So that shows that P transpose P is invertible, and this shows the proof of the lemma. So now we are going to characterize the equivalent partition among the partitions of T, and we will need them later in the interlacing part, this characterization. And this is from that book, lemma 9.3.2. So we say we have a partition, we have a graph and a partition, and the characteristic matrix of that partition. Then this partition is equitable if its column space is of P. The column space of P is A invariant. So A times P is Constantine. Oh, yeah, you see what I mean. And this is not so difficult, luckily. So we assume this is equitable. Then we have that AP is PB, which means that the column space of P is A invariant, because if I do A times a column of P, then it is the sum of a linear combination of the columns of P. That is the meaning of this equation. And now we assume that sorry, that the column space of P is A invariant, then AP is PB for some T times T matrix B. So then we have that this is that we have this equation because AP is PB. We don't know B, what is B, yes? So we know that a PBUJ is BIJ, as PUL is 1 if L is I and is equal to I and 0 otherwise. And this we can also calculate, that is just the number of neighbors of U in Cij. So that must be always a constant Bij, yes? So that is what. So this other, that means that the number of neighbors in Ci does not depend on the first U you take from Ci. Or that means the number of neighbors in Tj, I'm sorry, that must be Tj, not in Ci, I'm sorry. Hence, the partition pi is equitable. So one reason why you want to find equitable partition is you can find eigenvalues of a graph. And this is theorem 9.3.3 of that book I mentioned before. So let C be a graph with adjacent matrix A. Let pi is C1 to CD be an equitable partition of C. And let P be the characteristic matrix and B the quotient matrix of pi. Then the eigenvalues of, then the characteristic polynomial P divides the characteristic polynomial of A. So that means that if P has, say, 5 in multiplicity 3, then A must have 5 with multiplicity at least 3. For example. So we know that P is P transpose P times, then the inverse of that matrix times PTAP. Now we define the square root of PTP because that is a diagonal matrix. So what we do is we take the square root of the diagonal matrix. So this is also well defined because P transpose P is a diagonal matrix with positive elements, diagonal elements. Now you define P prime is the square root of PTP times B times square root of PTP and then inverse. I can first take the PTP minus inverse and then the square root. These two operations commute with each other, so it doesn't matter. They are the same matrix. Then you see that P prime is similar to B, and B prime is symmetric matrix. Yes? So we have B is diagonalizable, and we have a basis of eigenvectors with respective eigenvalue lambda 1, lambda 2 up to lambda t. So now we look at E P phi is B P. Because the reason why B is diagonalizable because that's exactly the same eigenvalues as P prime. So P prime is diagonalizable and hence also B. Yes, because similar. You can easily get a set of eigenvectors for B using B prime, the eigenvector of B prime. So that is what I did here. So he is not a mistake with the B. So that is what I meant to say. So I really mean the B. So we look at APVI. That's BPVI. Yes. And because the eigenvector for B, we get that lambda I times PPI. So that means that PVI is an eigenvector for A. Yes. So if we multiply now with this factor to the PVI, then we see that VI they are always linear independent because yes, it follows that the factors P phi are linearly independent. And this finishes the proof of the theorem. Okay, let now T be a graph. Let pi be an equivalent partition of T with quotient matrix P. We have seen that the eigenvalues of B are eigenvalues of T. Now we give a partial reverse. This is an unpublished result. So, but this is, I think, a very useful result. So now we assume that we have a collection of equivalent partitions so that for all vertices X there exists a partition pi I, such that it has one of the parts of pi I is X, the singleton X. And let Bi be the quotient matrix with Bi for I is 1 to S. Then for all eigenvalues theta of T that exists in J, such that theta is an eigenvalue of Pj. So we get this because we get that they are orthogonal if they are from different eigenvalues. So from different eigenvalues, they are orthogonal to each other, yes? So because A is the symmetric matrix, that's what I mean. Let Pi be the symmetric characteristic matrix of Pi with 4i is 1 to S. Assume that pi I has Ti parts and W1i to WTi is a base of Bi, yes, of eigenvectors. Then we blow up the eigenvector to get eigenvector for the matrix A. So you just multiply them by Pi, the characteristic matrix for the pi I. And they are eigenvectors of A and they are linearly independent. And the column space of this, the column space of Pi is equal to the space W spanned by those eigenvectors. Here to be P, I'm sorry. I should have said the P W1i up to P WTii. Because we have to have the same length. Otherwise, they have the W1T 1i has shorter length. So I meant here the PI W1 up to PI WITI. And they have the same dimension, those eigenvectors. Okay. So now we assume that we have an eigenvalue of T that is not an eigenvalue of any of those BIs. Then there exists an eigenvector W which is not zero, such that theta W is AW. Yes, that means that for all elements, it must be orthogonal to all the eigenvectors I already have for the partitions until now. Yes, the P1 to PS, pi1 to pi S. Yes. This means that W must be orthogonal to Pi for every characteristic polynomial or characteristic matrix of the partition pi I. Now we take X in C. Then there exists a J such that X, the singleton X, is an element of that, is a part of that partition. So that means that Wx must be 0. So we get a contradiction because the W is complete 0. And this shows the lemma. Okay, I think I have 10-15 minutes. So I will start with interlacing. I will not be able to finish interlacing, but I will start. So let's do interlacing. Let's see how far we come. So we have two matrices, an n times n symmetric matrix and an m times m symmetric matrix. And we have the n different eigenvalues of n eigenvalues of A and B and m eigenvalues of B. Then we say that the eigenvalues of B interlace of A if n, we assume that m is smaller equal to n, yes, that's there. If theta n minus m plus I of A is smaller equal to theta I of B is smaller equal to theta I of A. And why is this called interlacing? Because if you take m is n minus 1, then you get theta 1 A is greater than theta 1 of B is greater equal to theta 2 of A is greater equal to theta 2 of B, and so on. This is where the name interlacing comes from. And we say it is tight if there exists a J such that the first J eigenvalues of A and B coincide, and the last m minus J eigenvalues of B and A coincide. So that means that first J eigenvalues are all the same, and the last ones are all the same. This will be important to show that certain partitions are really not only we can show with this kind of tightness that certain partitions are equitable. So we already have seen the Rayleigh inequality. Yes, but I will. So that is okay. So we have an. So we have a symmetric matrix of order n. I'm sorry, I've forgotten. A must be symmetric. That is important. I'm sorry. And then we can see that oh, I see that I did not. So UI is the space. Did I not introduce this? Did I forget this? Yes, I forgot this. Okay, I'm sorry. This UI to be the space generated by the first U vectors, the U1 to UI. And the perp means the orthogonal complement. Yes? Then we get that it's always smaller equal to theta I plus 1. And if we quote your holes, then we know that W must be an eigenvector. W must be an eigenvector with eigenvalue theta I plus 1. So now we have the interlacing. So we have two symmetric matrices. Here's also an A. Okay. I'm sorry, there are many mistakes in this. So it should be theta n of A, not theta n of B. Okay. So we have an orthogonal. So now we take a matrix R, an n times m matrix that's R transpose times R is the identity matrix of order M. Then we take B is R transpose AR with θ1 to θm be an orthogonal basis of, and we have an orthogonal basis of eigenvectors V1 to Vm. I'm sorry, it has to be Vm. Then what we can show is that the eigenvalues of B interlace those of the A, and if theta I of B is theta I of A, then there exists y not equal to 0, such that By is theta A of y, and AR times y is theta I of A times R of y. So R of y is an eigenvector for A. So somehow the blow up kind of thing. That's what it means. And then we have 3 and 4. I will not. I will come back to this tomorrow. This 3 and 4, I will do that tomorrow. I will not come. I will try to prove 1 and 2, and then I stop, I think. So I will try. So what did I say? That the eigenvalues of B must interlace those of A. Yes. So I forgot to introduce this earlier. So the UJ is the span, the vector space spanned by the U1, U2J, and Pj is the eigenvector spanned by V1 to Vj. So clearly this dimension is always J, and R transpose Uj minus 1, that dimension is almost at most J minus 1, because dimension of Uj minus 1 is dimension J minus 1, and with the R we can sometimes it's smaller than this. So that means there exists a factor V which is not a zero factor inside Pi and R transpose Ui minus 1 perp. Yes? And then we can calculate this. So V transpose R transpose Uj transpose RV, the same because yes, it's 0. Yes. So, and then we get that RV is in Ui minus 1 perp, and RV is not 0, as if I multiply it by RT, then I get the V back. So it cannot be. So if this was 0, then V should be 0. Yeah. And it follows then by the Rayleigh inequalities that we get that theta I of A is greater or equal to theta I of B. And to show the other direction, we just observe that if I look at the eigenvalue of A, minus A, that's just the minus the n minus I plus 1 eigenvalue of A, and similar for B. So that is why we get the other inequality as well. Yes? I think I will stop here for today. I think you are all hungry for lunch. So I will start with part 2 tomorrow. Okay. Thank you so much.
Thank you very much, Professor Koolen. Any question from the audience? Any question? Okay, let's thank the speaker again. Thank you. See you tomorrow. Nice of you.
Okay, thank you. See you tomorrow.